Hello，大家，这一节视频我们是开始来讲序列模型，讲循环神经网络了。这个模型就会跟我们现在用的 chatbot 非常接近了。我们输入一段 prompt，然后这个 AI 模型就输出一段回复你的话，或者是说生成一段你想要的写给另外一个人的 email。这个里面，在视频开始之前呢，有几个 update。第一个是之前的暑期项目的研究 undergrad research project，我一共招到了7个人，一共有56个申请者，非常高兴，哈哈，这选到了一些成绩很好的学生，然后又有计算机视觉背景，和动画 animation 的背景，所以非常开心能够把我的一些博士论文的里面很想完成的事情，但是还没有办法，没有时间自己去做的，能够让这些本科生去做，很开心，哈哈。然后在是秋季学期，很可能我会去讲一门课，叫做自然语言处理，所以也会跟今天讲的循环神经网络非常接近。啊，这是一些 update，这当然这只是可能，还没有最后确定。Let's get started into the class. I'll start to share the screen. This part is the recurrent neural network. Here. At the beginning, we set up the environment and it requires us to do image captioning with recurrent neural network. In this exercise, we will implement vanilla recurrent neural network and use them to train a model that can generate novel captions for image. So this will be a toy dataset or toy model for us to understand the sequence model, which is um, predecessor of current powerful artificial intelligent chatbot. At the beginning, it loaded the dataset. We use the Coco dataset. They gave us several examples. Here is the separation of the training, validation, and the test. Inspect the data, we can print it out. See, this is the boy standing on a key skateboard in a street. So basically, it's that the we input this picture, and this picture will be converted to sequence of feature. This feature will have the same dimension of the input of the recurrent neural network. So we use this input to be the input feature to the model. This part we already used the pre-trained large model. For example, the BERT is a famous one. I think they use something fancier than BERT. As discussed in this lecture, the is for image captioning. Vanilla step forward. We open this file, RNN layer, PyTorch. This one. Let's put it in the front. Open this file that will implement the forward paths for different types of layers that are commonly used in recurrent neural networks. Note that since we use PyTorch, the backward path will be handled by PyTorch AutoGrad. That has been discussed in the last video. First, implement the RNN step forward. which implements the forward pass for a single time step. And step forward is this part. It say run the forward pass for a single time step of vanilla and use a tangent edge activation function. I have a picture of the tangent edge. This is tangent edge. Tangent edge is the blue curve, and the dashed red curve is the derivative of this function. Then the input data has dimension D. The hidden state has dimension H, mini batch size N. To do implement a single forward. Here we need to really know what RNN architecture is looking like. That's why I asked the question, reflection, what is RNN network? It's it's a network similar to this frame of RNN. In the slides, it shows a structure like this. This is input, this is the hidden layer, this is the output layer. If it's one to one, it's like that. In current task, it's a model of this many to many, and with the same dimension. For example, the picture transfer to three words. Say, I eat cheese. Then it will be I eat cheese. We expect the output to be exactly the I eat cheese. That will be 100% accurate. Then back to the code, we need to how did we get this line? This line is from here. We want to figure out something close to the slide L7S88. Hmm? Here. We want something like a equation like this. So we try to figure out the dimension of them and combine them together to this equation. I will walk you through the thought process of mine. First of all, I write this equation down literally from the PowerPoint slide. However, I find the dimension does not match. It says WX is DH, X is with dimension ND, H is NH, B is H. Then the next H is the next time steps hidden state will be with dimension of NH. You see, it does not conform to the multiplication of matrix. So I switch this to variable, say, then ND, DH will be NH finally. Then this part will align with the output. The same with the WH and H. You will get a NH result. That's how I figure out this line of code. I write it here. And after the correction by chatbot, I need to add a torch here to use the uh, to send those variables to GPU. Also use the tensor of the torch. That's the step of the RNN step forward. After that, we can hit run this block. It gives us the zero error. Then we, I raised the question here. The out equals use the toy example is too abstract. Here is a simple toy example of WX. WX, I think it's too ahead. I think that's some problem we meet later, we encounter later. Vanilla RNN step backward. Since we implement the forward, we do not need to implement the backward. It's handled by PyTorch. We can verify PyTorch autograd backward. So we just hit run that. It will give us the 100% accuracy. Is that the input for each sequence? Its length is t, then we have t hidden state. Okay. Okay, that's where I have the confusion of the dimension of those parameters. Let me start to throw these questions to you and think about that. L7 S80, why the dimension does not match? That's the question we have answered here. Refer to this slide, same with S80. My guess is this need to remove the, okay, we have discussed that. Then how to understand that the X as NTD, one sample has, okay, what do we mean by the NTD here? T is the number of red boxes in slide 16. This slide 16. The box number is 3, both 3. This is what question I have raised, and I finally answered it. The N is the batch size, which means, for example, we input 16 images to our current calculation circle, then this N will be 16. T is the number of red boxes in this slide. Also, the number of green boxes, blue boxes, which means the 3 word I eat cheese. The D is each word has a D dimensions word embedding, which means that's something related to natural language processing. That means the word I, they will have a word embedding. Let's say I have an example here. You see here, for example, it will have 0.1, 0.1, 0.5, 0.5. This long sequence will represent how the machine, how the artificial intelligence model understand the word I. The second word eat will be a different number. How do we get out this number? This is um, from they training something in a dictionary, and that dictionary works well by transfer those words into value those values sequence, and this sequence can represent this word. For example, if two sequences are very close, for example, eat and have, they both have the meaning of eating. So they will be close in the number, in the distance, if we calculate the distance between these two vector. That's the quick understanding of what is word embedding. Then the definition of RNN forward refer to this. That means we start to implement the RNN forward. We have discussed that the T, the length T is the number of words. Those are the thought process of mine. I have asked the chatbot and they reply with me. So I digest that and deliver it to you guys. If you are interested, you can read through my thought and my conversation with the chatbot. Next is the vanilla recurrent neural network forward. Now that you have implemented the forward for a single time step, we can do a for loop to do many time steps. Since recurrent neural network is using the same weight, but we do the calculation over and over again. So there will be many loops of the hidden layer. That's literally recurrent. Implement the function RN forward. This will be implemented using step forward. Okay, let's go to the layer RN forward here. We have discussed the dimension thing. I think you guys should be clear now. The H is a little bit special. H is the dimension of one single hidden unit. So H0 will have H dimension. H1, the next 10 steps, the hidden state will also have H dimension. This will help transfer it into the output or to the next layer or next time step of the recurrent unit. Then implement the forward pass for vanilla RNN running on a sequence of input data. You should use this function that you define above. You can use a for loop to help compute the forward pass. This is the initialization we got the dimensions from the input x and h0. H0 is a little bit special. The initial hidden state, it is given. You see that the one image, we got three word, I eat pizza. These three words are with the word embedding, and we use these three features to calculate, to predict the first word of the output. So H0 will be something similar. H0. Let me go. Let's go through that. It will discuss that very soon. Step forward. Since the length of this sentence, I eat pizza, it has three letters, so three words, so the T will be 3. Then we go do that 3 times, do the step forward. We got the H, we put the next H into the final long sequence matrix X. You see, comma, and time step that aligns with the H dimension here. Then we return the H. This is here, and you can ask yourself several questions. Now, at that time, I was confused with the H. What is H? What is the green box number? So H is the dimension of the one hidden state unit for one input sample. If we For n input sample, H0 will be NH, and the green box number is T. 10 step is in the range of 0T. Loop through three words in our example, not H. So we finally figure out the frame is this RNN frame. We're embedding X. N is the image. We have N images in a mini batch. T is one image is converted to T tokens, and each token has D dimension of the word embedding here. And after the conversion of the word embedding, those tokens are converted into those word embedding, you see. Then after we implement the RNN forward, we can run this block. We'll see error is 0. Now we have got the H, the hidden state of all we call it three green boxes. H is with the dimension of let's see, NH. That's H0. H is H hidden state of the entire time series. T is the length 3. N is the number of input image 16. H is the dimension of one single unit. Then vanilla RN backward. We don't need to implement that. We just run it. Got 0. Word embedding forward. That's in the word embedding forward. Give a X. Give the W. W is the weight matrix. V is the number of vocabularies, number of words in the vocabulary. My initial implementation is take out the parameters and then do this to for loop. It can work. For example, we loop from 0 to n is for each image, and then for what this image's first word, we look at this first word, then it's the first time step. We take this word index and give it to a variable index and use this index to get the word embedding. Then we put back this word embedding into the out, you see. The first image, first word, they will have this long word embedding 0, 0 0.1, 0 0.5, minus 0 0.5. Then do this in two for loops. We also can do it in this way. This is a much smarter way. It's using I have a note here. You see, it's a magic wind way to do that. X is the dimension NT. Then we imagine one image, one word. It will get the index of this one image and this one word to get the dimension D word embedding of this word, pass it to the out. I have an example here. I asked the chatbot to make examples. It will be easier to understand. It is shown. Put it to front. It's there. Use a toy example is too abstract. And this is what chatbot has said. My understanding is this way. It changes x to out by replacing each element of the x to the index out of w. So 0 becomes this, so on and so forth. Assume this is the embedding matrix embedding matrix W, and we have an input index this. Sequence 1 has word 0, word 2. Sequence 2 have word 2, word 1. Then after we run this, we see W0 will becomes a word embedding of this two number. Then we put back this two number into the position of the 0. The same for W2, W2, W1. Then it will become a matrix like this. That's the whole process of the simplification. After that, we can know the word embedding has been implemented. We run that, we find the out error is 0. Also here backward is 0. How does word embedding connect to vanilla RNN? That's also a question I have asked. They have this sequence, this pipeline flow. First, the word index, it has the shape of NT. Then the word embedding, look at this record dictionary. Then we got the out of these two. Then we send this embedded vector as the input to the vanilla RNN, pass as the input X to RNN forward. That's the relationship. At each time t, you slice the embedding tensor to get the current word vector. See here. Shape ND. So we handle n picture at a time. And each word has dimension of d. So we look at this first column. This first column, we have n pictures handling at the same time. Each picture has d dimension for this word. The second picture, first word has d dimension. The third picture's first word has d dimension, so on and so forth. We pass this xt to this equation we have implemented before. We got the wxd into hidden dimension h. The dimension of d, we can check out the previous process. It has been written there. Summary, the word embedding layer acts as a translator. It converts abstract word IDs to meaningful numerical vectors D, which are then directly consumed by RNN to maintain sequence context over time. Temporal affine layer. At each time step, we use a affine function to transform the RNN hidden vector at that time step into a scores for each word in the vocabulary. That means this part, after we have got the hidden state, we use this hidden state to predict one word and use this word to compare with the ground truth. Then we got a loss, and we use this loss to backpropagate to correct the weight of this hidden layer. Run the following to perform numerical gradient check on the implementation. You should see errors 0, temporal affine forward. Here. Now this is simple. I think they have implemented that for us. We don't need to do anything. We just run this box, got the zero temporal softmax loss in an RNN language model. At every time step, we produce a score for each word in vocabulary. We know the ground truth word is at time step, at each time step, so we use this to calculate the loss. Yes, just as I have discussed, now we need to, they have implemented that for us. I raised one question, produce a score for each word in the vocabulary. This is massive. 1,000 word in vocabulary is more than 1,000 scores. Imagine the real chatbot is even larger. Yeah, that's a comment of mine. Question is, we are doing image capturing. Why the input is word? What is the input and output of RNN? That's also a question we can think about. Actually, we have discussed that in the previous question. We have converted the image into the feature. Image capturing is a generative task. To generate the next word, we feed the previous word as the input to the RNN at each step. How the image entered the RNN. The connection between image, word, and RNN is the initial hidden state represents the image. So the first green box in the picture. Before RNN starts reading caption words, it needs to see the image. It goes through the pre-trained convolutional neural network, pass this image feature through a linear layer to map them to the hidden size edge. Use this vector as the initial hidden state. The RNN's memory starts off containing information of the image. Input sequence represent the word. At each time step t, the input x is the word embedding of the current word. Visual diagram, linear layer, initial state, start. Okay, you see, start, and the initial H0 will be passed to here. And this is a start. That's how the information of the picture comes. It comes to the H0. So the H0 will come through all this line. And we run that, it gets the correct result. We don't need to implement anything here. Yeah, they have written that, they have done that for us. Just understand this pipeline will be good. And for image capturing, now that you have implemented the layers, we can put them together to a class. Implement the forward pass in the loss function. Captioning RNN. Let's go to that. Here. Hmm? Captioning RNN. Oh, it's this one. Captioning solver PyTorch. Huh? PyTorch. PyTorch. That's another file. PyTorch. Should have opened it somewhere there. Here. on PyTorch. And this is the part we need to implement. Now that we have implemented the necessary layer, we go to this class, implement the forward pass of the model in the loss function. Now, for now, you only need to implement the case where equals RNN. You will implement that later. Actually, will not. After doing so, running the following to check your forward pass. The task now is to implement the loss, computing chaining time loss for and we input image features and ground truth captions for those image. Yeah, now here is a little bit different. We we have these captions, but we leave the leave out the last word of the caption as in captions in, and we don't give the first word for the caption out. Cut the caption into two pieces, have everything but that. Okay. When we will do that, we'll discuss that later. You'll need to do this. Wait. Those are already given. The implementation is implement the forward pass using a fine. Yeah, we use this affine layer to see we input the feature W pro B project here. Then we got the initial hidden state. Then we input the captions in. Use a word embedding layer to wait, affine forward. Oh, it has written this to me, so we don't need to implement that ourselves. It's in the layers. Okay, we just call this function from the layers. We don't need to implement it this way. Then I use a word embedding layer to transform the word into in captions in from index to vectors. Captions in, that's all the word except the last one. We convert that into the input word vector and put that into the RNN. Got the hidden state vector. We pass this hidden state vector to predict the blue box in the diagram. And we calculate the loss of the blue predicted word and the predicted word and the ground truth word, which is here. So you see, in the chaining part, we have the ground truth, and we use that ground truth to as the input into the next time step. We will not do the same in the testing set. After this implementation, we run the sanity check. We find the loss is correct. Run the following cell to perform the numerical check. This is verify the back propagation overfit small data. Similar to solver class we used to train image classification models on the previous assignment. It's just calling the API. it directly runs this part. We don't need to do anything. It overfit 100 samples in the small data set. So we'll see the training loss gets down very quickly. And see the final loss is 0.01. And we now implement the test set. The test set, it requires us to implement this sample. Here, the different part is, this is the same. We do the same as the training set. We need to update the edge state previous. We record the current word in, the current word is a column vector. It has n dimensions, n rows, and one column. Each of the one column will be the start. This start will, for example, be the word index 1. It's only a placeholder, but we have an index for it. Then for the max length, we run through, max length is the number of the green boxes, blue boxes, and red boxes. Input one word, we get the input word vector, put that into the RNN step forward. We get this time steps hidden state vector. Now we do not use a temporal affine award because now we are not handling them in a large vector. We handle it one word by one word. So we predict this current hidden state value and use that to calculate the score for the blue box. And we use a max function to find the index of the largest probability word from the vocabulary. Put that into the caption. Assume that we have found the correct word and use it as the input for the next 10 step. Then this for loop, when this for loop is done, we output these captions we predicted. Then we see that in training set, we get very good. It's almost the same result with the ground truth since we overfitted it. However, in the test set, it will not make sense. It gives the word wall, then end. Gives the word a man bass eating with the skis since it's overfit. So we don't need to worry that too much. We have implemented the whole pipeline. That's enough. The last inline question is whether it's good we use character-based embedding. I made the same question in the in the natural language processing course. I think the reply is almost the same. I say you have lighter weight matrix. Also, disadvantage is that it's less expressive. And this is the correction by chatbot. Okay, that's the all the content of this video. Hope you have a better understanding of the recurrent neural network. It's a powerful tool. We are moving step by step closer to the current state of the art. See you in the next video. Bye.